Good evening to all of you. Yeah, we will have a keynote speak by Professor Nilanjan Chakraborty on the title Direct Numerical Simulations Based Analysis of Premixed Flame Wall Interaction and Heat Transfer Characteristics in Turbulent Boundary Layers. Okay, so Professor Nilanjan Chakraborty is working as a professor in fluid dynamics and the lead member of the Fluid Dynamics and Thermal Systems Research Group within the School of Engineering in Newcastle University. Previously, he was a senior lecturer and a lecturer at the University of Liverpool and a mechanical engineer of General Electric Research and Development Division before he pursued his PhD and postdoctoral research at the University of Cambridge. His research interests include direct numerical simulation of turbulent combustion and multi-phase flows, large eddy simulations, combustion modeling, natural convection of non-Newtonian fluids, melting and solidification related heat transfer problems in classical manufacturing, especially in welding, and laser aided manufacturing applications. To date, his research has been funded by Nuffield Foundation, Newton's Grant, and British Council and Engineering and Physical Science Research Council UK, and other. He has got many projects in that company. And in 2005, he and his co-authors were awarded with the prestigious Gaydon Prize for most significant UK contributions to the 30th International Symposium on Combustion. He has awarded the Hans Wood Prize by the British section of Combustion Institute for his contributions to combustion science in 2007. A paper co-authored by him was judged to be the most significant paper presented in the droplet combustion in combustion colloquium of the 32nd International Combustion Symposium. Professor Chakraborty is one of the recipients of the prestigious Hind Ratan Award in 2015, which is one of the highest Indian awards given to the people of Indian origin for outstanding contributions in their field of work by the non-resident Indian Welfare Society of India, an organization under the umbrella of the Indian government. In addition to that, he has got many accolades to his credit. So it is a long list here. I don't want to waste the time because we will listen to his lecture. That will be very interesting. So I request Professor Nilanjan Chakraborty to go ahead with this lecture. Thank you, Professor.
Thank you, Mr. Chair. Thanks for the kind introduction. So it's my pleasure to present this talk in the 26th and 4th International ISHMTAST-FE Heat and Mass Transfer Conference. Today, I'll talk about direct numerical simulation-based analysis of premixed flame wall interaction and heat transfer characteristics in turbulent boundary layers. So flame wall interaction, it involves rich interplay between heat and mass transfer, turbulent fluid motion, chemical thermodynamics, chemical kinetics. So it's intellectually very rich process. Essentially, one actually deals with three-way interaction, and you can consider as a three-way feedback mechanism between flame, wall, and turbulence, where each one actually affects the other. Now, flame wall interaction occurs in many flows of engineering interest in IC engines, gas turbines. And why this is important? Because spatial and temporal fluctuations of wall temperature induce thermal stresses and strongly affect combustor lifespan. And it is becoming increasingly important for new combustors because they are made smaller in size to increase energy density and reduce weight, and especially in the case of hybrid engines in the context of electric powertrain, combustors are made smaller in size. And in the case of microcombustors, the main problem is because of the high surface to volume ratio. Because of the heat transfer through the wall, flame more readily quenches. So in order to actually design high quality hybrid engines or microcombustors, we need to actually understand the flame wall interaction accurately. Now, traditional combustion models are mostly devised for flows where combustion takes place away from the wall. wall is almost non-existent in the most of the combustion modeling literature so far. However, if we actually have to consider flame wall interaction in the case of development of the new generation combustors, we have to consider the presence of wall and the effect of wall on the reaction rate closures in the context of Reynolds average Navier-Stokes or large eddy simulations. And that's where we are coming. So I'll give a very, very brief introduction to direct numerical simulation of what it means. This is the traditional energy turbulent kinetic energy spectrum diagram. Here, the kappa is the wave number, which is inversely proportional to the length scale of turbulent eddies. In the case of direct numerical simulation, we resolve up to this point. Please note, as the kappa increases, length scale decreases. So we actually resolve up to a length scale, which is commonly known as the Kolmogorov length scale, which is the smallest length scale of turbulence. So the grid size needs to be smaller than the Kolmogorov length scale. In the case of Reynolds average Navier-Stokes simulation, the grid size remains of the order of the integral length scale, where you get the highest value, more or less, for the energy spectrum. Now let's try to actually visualize how it actually works based on a simple jet flow. If you carry out DNS, you will get this kind of picture for the instantaneous mixing field. If you do RANs, you will get this. So clearly you can actually appreciate there's a loss of information from here to there. However, the physical information doesn't go away. You have to represent that physical information through models. Now, model is a glorious name for approximation. So the fidelity of this kind of simulation depends strongly on the accuracy of the models. And large eddy simulation falls somewhere in between. So anything from here onward is actually unresolved in RANs, and that needs to be modeled. In the case of LES, it needs to be modeled for this part. And in DNS, I have exaggerated this part, but nothing interesting happens here. Effectively, viscosity transforms the kinetic energy to heat energy, nothing else. Now think about an analogy of sports photography using your phone camera. If you actually try to photograph an athlete running using your phone camera, you will get a smudged image which is similar to this. Effectively, what you are getting, an averaged picture over your exposure time. Now, if you reduce your exposure time, you get a sharp image like this, but obviously, in order to reduce your exposure time, you have to invest in an expensive camera. So same applies for computational requirements. RANs simulations are cheap. That's why it's mostly used in industry. DNS, it is expensive. The computational cost scales with almost Reynolds number cube. In the case of DNS, all the length scales and time scales of turbulence are resolved without any recourse to physical approximation. RANs, as I mentioned, depends on the modeling accuracy. LES, the modeling implications are less severe in comparison to RANs. So DNS so far has been limited to academic applications and for simple configurations, but the physics that one can actually obtain from the direct numerical simulation, that can be used for the purpose of development of high fidelity RANs and LES closures. So first, I'll talk about a very simple configuration of flame wall interaction, which is called head-on quenching configuration. Here, flame normal aligns with the wall normal direction. So for the time being, don't look at the animation. Here I have an isothermal wall. Here I have cold gas. Here I have reactants. Here I have products. The flame moves towards the wall. Let me introduce some variables here. First is the reaction progress variable, which is defined based on a mass fraction of a species alpha in this manner. The subscript 0 stands for the values in the unburned gas. Infinity stands for the values in the fully burned gas. The way it is defined, the reaction progress variable increases monotonically from the unburned, from a value of 0 in the unburned gas to unity in the fully burned gas. Similarly, I can actually define a non-dimensional temperature where this is the instantaneous temperature, unburned gas temperature, and T adiabatic is the adiabatic flame temperature. two quantities are very, very important from the point of view of flame wall quenching. One is the normalized wall heat flux. Here, rho 0 is unburned gas density, Cp0 is the specific heat at constant pressure in the unburned gas, SL is the laminar burning velocity for premixed flame. Peclet number, I know that Peclet number is defined in a different manner in the heat transfer literature, but one can actually get the equivalent form. And this is the form which is used for flame wall interaction, where X is the wall normal distance of a given temperature isosurface, non-dimensional temperature isosurface, and is the flame thickness. Now, I have considered T equal to 0.9 isosurface because in the unstrained laminar premixed flame, maximum heat release takes place around this for methane air flame. So let's look at the animation, but beforehand, I will tell you how reaction progress variable evolves with time is shown here. Non-dimensional temperature evolves with time is shown here. This is the reaction rate. And these two are the temporal evolutions of the heat flux and the Peclet number. So let me go back, and now you can see flame is approaching towards the wall. When flame is away from the wall, C and T are identical, but as soon as the reaction rate goes to 0, the coupling between C and T is broken. Once again, you can see when the flame is away from the wall, the heat flux is 0. But as the reaction rate goes to 0, that you get the maximum value of wall heat flux. That instant coincides with the instant when the Peclet number is the smallest. And after that, the isotherms actually diffuse away from the wall. And as a result, the heat flux drops, Peclet number increases further. Now, one non-dimensional quantity plays a very, very important role in this behavior. That's Lewis number, which is given by the ratio of thermal diffusivity to mass diffusivity. And let's see what really happens. Whatever I mentioned earlier, it is shown here. And two quantities are of primary interest: the maximum value of normalized wall heat flux and minimum value of Peclet number, because this gives us the measure of the quenching distance, and this is the maximum heat flux value. Now, Lewis number 1 is representative of stoichiometric methane air flame. Now, let's see what happens when Lewis number changes. So Lewis number 0.8 is representative when I have 20% hydrogen by volume blended with methane with an overall equivalence ratio of 0.6. And this is representative of a ethane air flame with an equivalence ratio 1.2. But if you look at the minimum Peclet number and maximum wall heat flux, one can see the minimum Peclet number actually decreases with increasing Lewis number. Just the opposite trend is observed for the maximum wall heat flux. What really happens when Lewis number is smaller than unity? The thermal diffusion is weaker than the mass diffusion, so the reactants actually diffuse faster into the flame than the heat diffuses from the reaction zone. As a result, the isotherm based on which the Peclet number is defined remains away from the wall when the flame quenching takes place. Just the opposite thing happens for Lewis number 1.2. So if we look at what happens in 3D flame while quenching under turbulent condition, exactly similar behavior. So qualitatively, the behavior remains the same, but Lewis number affects it significantly. The first important thing to note that in the case of Lewis number 0.8, so if we take hydrogen blended methane flame, the maximum wall heat flux can be much greater than the maximum wall heat flux obtained under the laminar condition. What happens to the quenching distance? Quenching distance can go below the minimum quenching distance under the laminar condition. What's the reason? Let's look at these kind of wrinkles under the turbulence. Here, the flame is convex towards the reactants. Here, the focusing of fresh reactants take place at a faster rate than the defocusing rate of the heat from the reaction zone. So effectively, in these zones, you have high reactant concentration and high temperature. So these zones actually burn faster. In actuality, you can actually obtain super adiabatic temperatures in these zones. As a result, these zones are more resistant to quenching, and they can actually reach closer to the wall before quenching, and that gives rise to the higher heat flux and lower quenching distance. Just the opposite thing happens where flame is concavely curved, but these zones are away from the wall, so they really don't affect the maximum wall heat flux and minimum Peclet number. Lewis number 1.2, just the opposite thing. Now the defocusing rate of heat takes place at the faster rate in comparison to the focusing of reactants into the reaction zone. So here I have less concentration of reactants, low temperature. So these zones actually quench more readily. So here the maximum wall heat flux remains more or less comparable to the laminar value. Quenching distance remains comparable to that in the laminar case. Now, so far, whatever I discussed is based on single-step Arrhenius type irreversible chemistry. How chemistry plays a role in the flame wall quenching, especially in the case of head-on quenching. So if you look at the non-dimensional temperature distribution with time, qualitatively the same. If you look at reaction progress variable distribution between single-step chemistry and detailed chemistry, they are same. One thing to note, in the case of isothermal wall boundary condition, because of Dirichlet condition, the temperature remains 0 in a non-dimensional form at the wall, where x equal to 0. Whereas in the case of species, wall normal flux is 0. As a result, when the flame quenches, reaction progress variable still increases because the unburnt reactants actually diffuse to the interior of the domain. Omega C is the normalized reaction rate of reaction progress variable. As the time progresses, it actually drops to 0 because of the flame quenching. In the case of single-step chemistry, the normalized heat release rate and normalized reaction rate, they are qualitatively similar. That is no longer the case for detailed chemistry. One can actually see there is quite a bit of heat release at the wall, even when the reaction rate has gone to 0 for the reaction progress variable, which is defined based on the methane mass fraction here. What really happens? You have species like HO2, H2O2, which are available within the flame. Now, when the flame quenches, you still have that swoop of intermediate species, and species like H2O2, HO2, they can react at low temperature, and that can actually give rise to this wall heat release. Now, if you look at the instantaneous reaction rate, they are given by this kind of generic expression. You can appreciate it's a highly nonlinear function of temperature. As a result, whether you consider mean in terms of Reynolds averaging or filtered reaction rate, it is not a function of Fevre mean temperature. Fevre mean is a density weighted mean given in this manner. As a result, this kind of function you cannot actually use for modeling the mean reaction rate. In the case of RANS, this quantity goes to the average value of the molecular diffusion goes to 0, and one often actually uses this kind of expression to model the mean reaction rate. Effectively, in this approach, we model the flame surface area to volume ratio and assume that per unit surface area, the reactant consumption is similar to that of a laminar flame. So let's see how it actually works. This is the flame surface density. This is the conventional model. And you can see when the flame wall interaction occurs, whether you use single-step chemistry or detailed chemistry, the conventional model significantly over-predicts the reaction rate close to the wall. So the scalar gradient doesn't go to 0 at the wall, whereas the reaction rate does. And as a result, the conventional model fails. We have modified that model where we actually involved the minimum quenching distance explicitly into this model expression. There are small discrepancies, but in the Reynolds average context, that's not unusual. At least it does much better job in comparison to the existing model. what happens to hydrogen flames? Now, why hydrogen flame? Because hydrogen is actually considered from the fuel for the future. In the UK, we are moving from the standard hydrocarbon fuels to hydrogen fuels to reduce greenhouse gas emission. So first, let's look at methane air flame. When the reaction rate drops, I still have heat release at the wall, as I mentioned earlier. This behavior in the case of hydrogen air flame and for the normalized reaction rate is qualitatively similar. But if you look at the wall, if you look at the heat release, as it progresses with time, the heat release is significant at the wall, although the temperature is the lowest at the wall, and this heat release rate is comparable to the heat release which takes place within the flame when the flame was away from the wall. So obviously, the mechanism by which this heat release takes place at the wall is different from the heat release which happens within the high temperature region within the flame. I mentioned about the species like HO2, H2O2. Those are more abundant in hydrogen air flame in comparison to hydrocarbon air flames. But in addition to that, at the high temperature zones, you get radicals like H, OH, which play an important role in terms of the chain propagating reaction. Now, although when the flame quenches, we still have those intermediate species, and they can actually still give rise to chain propagation reaction even at low temperature, and that can give rise to significant amount of wall heat release. Implications for that. So the model that I mentioned earlier, let me show it here again. One can see the conventional model really does not capture the mean reaction rate. The model that we came up with that works both for methane air flame as well as for hydrogen air flame. However, it is relatively easier to actually model the reaction rate of reaction progress variable because that's based on major species mass fraction. But it is not really easy to actually model the wall heat release in hydrogen air flames because of the major role played by the intermediate species. It is really, really new finding from a very new publication. There's a lot to be done in order to actually model hydrogen air flame wall interaction for next generation combustors. So now I'll go into some discussion of flame wall interaction in turbulent boundary layers. We considered two configurations. Here is a rod stabilized V flame. We kept the flame holder closer to the bottom wall so that it more readily interacts with the bottom wall, whereas the flame wall interaction for the top wall takes place at a later stage in terms of the streamwise distance. It also enables us to actually compare the upper branch with the lower branch. H here is the channel half height. Took us about 500 million grid point. It's a representative of a methane air flame. This is another alternative configuration with a periodic channel flow. Again, H is the channel half height, but we chopped the top of the channel for computational economy. Even then, it involves about 0.25 billion grid points. On Cray XC30 in the architecture, these two simulations involved about 1,500 processors for almost 25 to 35 days continuous runtime. So these are really, really expensive simulations. How do they look like? This is the C equal to point isosurface. And you can see this is the non-dimensional temperature. Here flame hits the wall. You can probably see that the thermal boundary layer developing in this. Q is the second invariant of velocity gradient tensor, gives us the mesh, a kind of an indication of the vertical structures. One can see if somebody looks carefully hairpin vortices, but as the time progresses here, flame quenches. That's why you don't have that red isosurface everywhere. One important thing to notice, this is a statistically stationary configuration, whereas this one is statistically unsteady configuration. So once again, this is the time evolution of how quenching happens. Please note we have carried out these simulations for both isothermal as well as adiabatic wall boundary conditions. In this case, in the case of head-on interaction, in the case of isothermal wall, it ultimately quenches. In the case of adiabatic wall, ultimately flame does not stay within the domain because it actually consumes all the reactants as it approaches towards the wall. Boundary condition plays a very, very important role. You can see from the isosurface here that the flame is stretched towards the streamwise direction in comparison to the adiabatic wall. If we look at in an average sense, you can see these isosurfaces of reaction progress variables are bent towards the upstream. What really happens, reaction rate is 0 on the wall for isothermal case. For adiabatic case, actually reaction can take place on the wall surface. As a result, flame tries to go upstream, but in this particular case, upstream flow is greater than the laminar burning velocity so that it cannot propagate. In the case of V flame, this is the situation in a mean sense. So thermal expansion takes place in mainly in the flame normal direction, which has a component in the mean flow direction. And that sets up a stronger velocity gradient. As a result, on the reacting condition, the friction velocity actually increases in comparison to the non-reacting case. And this trend is more prevalent in the adiabatic case because flame does not quench, the thermal expansion effects are stronger. However, in the case of head-on interaction, the friction velocity with respect to the non-reactive friction velocity decreases as the flame wall interaction takes place. In this case, flame moves like this. Thermal expansion effects are mostly in the wall normal direction. As a result, the redistribution of momentum from the streamwise direction to the wall normal direction gives rise to this drop. But this drop is less stiff here in the case of adiabatic case. So wall boundary condition plays a very, very important role. Orientation of mean direction of flame propagation with respect to wall normal, orientation of flame normal to the background flow direction, all of them are very important in the case of flame wall interaction in turbulent boundary layer. So what happens to the textbook material? If we look at the log law really falls down for flame wall interaction. This relation for the viscous sublayer still holds. What happens for the thermal boundary layer? The well-known relation based by Case and Crawford falls miserably here. So effectively, all the textbook materials in the heat transfer literature are invalid in the case of flame wall interaction. Why that's the case? In order to actually demonstrate that, I'll go into boundary layer flashback just as an example for hydrogen-rich premixed flames. And I'll take the turbulent kinetic energy transport equation. So this is how the equation looks like for premixed flames. This is commonly known as the turbulent kinetic energy generation term, which I absolutely don't like. I want to call that the mean velocity gradient term. Why I don't like, I will explain in a couple of minutes. This is the term which is identically 0 in the case of incompressible flow. This is the pressure dilatation term, which is identically 0 for incompressible flow, but it plays a very, very important role in premixed flame. This is the combined interaction of the molecular diffusion and dissipation term. This is the pressure transport. This is the turbulent transport. This is how the flashback in hydrogen-rich flame in the turbulent boundary layer looks like. Again, once again, these are the Q values. This is the T equal to 1,700 K isosurface. These green zones are the zones where the flow reversal takes place because of the flow diverges ahead of the flame, and that sets up adverse pressure gradient. If we look from the top view, in these white zones, you have negative shear stress. Now let's look at turbulent kinetic energy and dissipation in the log form. And if we look at how it is distributed over C tilde, with the Febvre average reaction progress variable within the flame, the maximum value is obtained close to the wall because of the wall shear, whereas in the case of dissipation, it monotonically decreases from the wall to the middle of the channel as expected. Now, this is commonly referred to as the production term in the literature. Look at what happens to the production term. It is negative. So in other words, it doesn't work like a production term. It works like a sink to turbulent kinetic energy. As a result, the local equilibrium between the production and dissipation, which is often invoked in the non-reacting turbulent flow, that falls completely in the case of flame wall interaction. It is rendered invalid in the case of a flame wall interaction for turbulent boundary layer, and this is the prerequisite for derivation for log law. And that's why the log law really doesn't work in the case of turbulent premixed flame wall interaction. Now, with that, I will go into another material where we will talk about the interrelation between turbulent burning velocity and wall heat flux using energy integral equation. So those of you who have taken convective heat transfer courses, they have already seen this equation several times, but here we have an extra term which comes because of the mean reaction rate. And in this case, H stands for sensible enthalpy. And once you actually integrate these terms between two locations in the streamwise direction, one gets this equation. Obviously, NUL is the Nusselt number. A projection is the projected flame area. ST stands for the turbulent burning velocity, and A segment is the area on the wall. So we have considered steady state energy equation for the free flame, which I showed earlier. This is the definition of turbulent burning velocity. T1L, T2L are defined in this manner. Minus sign for Nusselt number because we are actually losing heat through this bottom wall, and that's taken care of by this negative sign. Nusselt number is just the magnitude. So first important thing to notice that we have seen, we have evaluated each of these terms at this location, 6, 7, 8, 9, 10, in terms of the streamwise location normalized by the channel half height. T1 plus T2 remains equal to T3 plus T4. T2, the free stream temperature variation term, is negligible in this case, so we can actually ignore that for this particular configuration at least. Here I am showing the reaction rate closure that I mentioned earlier. The first thing to note, these vertical lines are the edges of thermal boundary layer. So first thing to note that the reaction rate actually takes place within the thermal boundary layer. What happens to the model performance? It does reasonable job away from the wall, but as soon as the quenching starts, there is quite a bit of discrepancy. Please note this model was proposed for head-on quenching, and here we are dealing with oblique flame quenching. So obviously, there is a huge scope for improvement of this kind of models for general flame wall interaction. The implication of that model inaccuracy is that if we look for turbulent flame speed between these two zones, these two zones, these two zones, and these two zones, there can be local discrepancies. The discrepancy is relatively high, close to the leading edge of thermal boundary layer, because thermal boundary layer starts around this region. But when you actually integrate from 6 to 10, they are in reasonable agreement. Now, once we understand that, this is the integrated form of the energy integral equation. And if I put the ST from the DNS data, I can get these blue values for the normalized Nusselt number. And if I put the modeled expression of turbulent burning velocity as shown in the previous slide there, there can be quite a large discrepancy, especially towards the leading edge of the boundary layer. But when you integrate from here to there, the agreement is relatively good. However, that brings some uncertainty. In other words, it is probably not a good idea to actually estimate Nusselt number in the case of flame wall interaction based on the turbulent burning velocity. One thing to note, based on this equation, it is clear that turbulent burning velocity and Nusselt number are not two independent parameters in flame wall interaction. If you know one, you should be able to find another. T1 L and T2 L are functions of mean variations of velocity and temperature within the thermal boundary layer. They're relatively easy to measure experimentally. Experimentally, it is relatively easier to measure the wall heat flux. So if one can actually measure these three quantities, it should be possible to actually measure the turbulent burning velocity within the thermal boundary layer. Experimental diagnostics of turbulent burning velocity directly in thermal boundary layer in flame wall interaction is impossible almost, because the temperature changes by 800 K in a span of 1 millimeter. Very often the flame quenches 1 micron distance from the wall. But this actually gives you an insight how one can actually use the experimental data to estimate turbulent burning velocity. And that brings me to the conclusions. The mean behavior of velocity and temperature are significantly affected by flame and flow configuration in flame wall interaction. Standard formulations of RANS and LES need to be revised to take into consideration of the flame wall interaction effects in the boundary layer. Production dissipation balance in turbulent kinetic energy equation does not necessarily hold during flame wall interaction. Turbulent burning velocity and Nusselt number are linked. They are not independent parameters, but if one has measurements for mean velocity and temperature and wall heat flux, that can be used to predict turbulent burning velocity. Prediction of major reaction rate of major species is not sufficient for hydrogen-enriched flames, especially from the prediction for heat release rate. So we are working on several aspects on flame wall interaction. The future direct numerical simulation data will involve higher values of Reynolds number, friction Reynolds number, more involved chemical mechanism, flame wall interaction in laboratory scale configuration, conjugate heat transfer. We are in the process of using DNS data to develop high fidelity turbulence models, velocity and temperature wall functions for flame wall interaction, because I showed that usual log-law based wall functions don't work in flame wall interaction. We are using machine learning technologies based on the DNS data that we obtain for flame wall interaction modeling, and we use these things for hybrid RANS LES for flame wall interaction. So lots to come in the future. I'm grateful to my collaborators and co-authors which made this research possible, and the funders for who actually provided the computational means and funding for enabling this research. Thank you for your attention. I'll be happy to answer any questions that you may have.
Thank you, Professor Chakraborty. We'll wait for the questions. I have not seen any questions so far. Is there any question from the audience? We get some questions. I have a curiosity about your machine learning approach with the DNS. So how you are generating the data by doing the DNS?
Well, direct numerical simulation is used for the kind of results that I showed here. And once you actually have the direct numerical simulation data, you can actually have temporarily resolved, spatially resolved DNS data, which you can almost consider as experimental data with that kind of resolution. You can use a part of that data set for different parameters to actually train your machine learning techniques, which can be artificial neural network, it can be genetic programming. And based on that training, you will come up with certain expressions. And then what we try to do, that we actually keep a part of the data separately. So during the training process, our algorithm has not seen that data. So we actually try to see whatever we have come up with based on the training, whether those functions can actually predict the behavior for the portions which our machine learning algorithm didn't see previously. And then it comes actually to use them for practical RANs or LES applications.
Okay, yeah, I see. And then in another conditions which we have not done the simulations, how you're expecting that the results will match? Like when it is completely different.
Well, that's a good point. For that, obviously, you cannot take any arbitrary function which is spit out by the machine learning. What you have to do, just like before machine learning, when you actually develop model, that was determined by the physics, right?
Exactly.
Yeah. So
that's where I'm coming.
So you can actually use machine learning either unsupervised form or supervised form. Now, depending upon what you want to do, sometimes because of the chemistry part is actually relatively easy. You can actually do it in an unsupervised form. Turbulence is not so easy. Yes. So very often you actually have to give additional constraints which are coming from your understanding of the physics. And that is sometimes coming based on the post-processing that you have done for the direct numerical simulation.
Exactly.
Already. So you actually tell the machine learning algorithms to actually follow certain constraints. It is extremely, extremely important because, as you mentioned, we are going to do these things for different kind of flows in a practical application. And unless they are actually physics informed, there is no guarantee that they might actually work in reality. Whereas traditional combustion models or traditional turbulence models are based on physics. So
that's where I have the curiosity, like how it will work.
It is more important in flame wall interaction because probably you have seen that the flame configuration and flow configuration can change the behavior tremendously. And you cannot tell a priori that whether you are going to have head-on interaction or oblique interaction in a practical geometry. So that's why the physics-informed aspect is extremely, extremely important.
Thank you. Yeah. Thanks for the nice talk. I have learned a lot from this talk. Thank you.
Thank you.
I am not getting any questions from the audience. So I hope there are no other questions. So with that, we'll end the session here.
Thank you.
Yeah.
Thank you.
Thank you.
Thanks.
Thanks.
Bye.